So my name is Martin Kronbichler. I am one of the people who is most active in terms of the HPC parts of deal.II. And I want to show you a few things, like a few motivations why we have this module, which is a bit special, and HPC related activities that we have in deal.II. So what I'm going to show you is that we're what is a matrix-free method, just for those of you not familiar with that term. I show you a few use cases and the multi-grid framework of deal.II. So when you look at HPC today, you will see that most of the talks in HPC are going to how do we go to exascale. And what is exascale? Exascale, it would be computers which can do 1 exaflop per second, which would be 10 to the 18 operations in 1 second, double precision floating point operations. And people are expecting to get there maybe next year or in 2 years, depending on how good the installations go on. And what we want in deal.II is we really want to have the user utilize this power of the largest machine in the world. And we want to have this infrastructure not just large machines, but we also want to use them in a smart way. So we want to have efficient discretizations. We want to have efficient solvers like multigrid, as I already mentioned. And of course, that means that we solve for 10 to the 9, 10 to the 10, 10 to the 11, 10 to the 12 unknowns. We have many, many time steps. So really need the optimal complexity ingredients. And of course, since we're talking about modern hardware, exascale, a lot of the floating point operations that we get today are not coming from traditional scalar instructions, but you need vector instructions like SIMD, you need GPUs, you need some modern architecture. So there's a lot of things that we need to do here and that we want to provide. And I will come to that figure I show in the picture later, but I just want to go on now. Of course, for us as a library, there's always the decision, how do we implement things? Are we using external libraries, which are specialized, for example, in linear algebra, or are we implementing it on ourselves? Linear algebra, of course, Betsy, Trillinos, that's the things we have developed, included in deal.II for a long time already. And of course, the same is for the mesh partitioning. That's something we're not specialists in, but we want to use because we are specialists in finite elements. And of course, specialists does not mean that we don't do certain things. For example, we have implemented our own linear algebra infrastructure in deal.II because sometimes the functionality we get from external packages is not adequate in terms of functionality, not in terms of performance, depending on what we need. So we have specialized MPI parallel vectors, which are used under the hood for the results I'll show you later. We have SIMD instructions, and so we have some GPU related stuff. So we really want to focus in several things here. So that's the main part. And of course, what we try to deliver as a library is that we serve our users so that they can concentrate on the application. Of course, we always invite people to contribute, as Wolfgang said before, but we also want to deliver something which is useful. And so that brings me to my topic here. So I'm one of the main authors in the matrix-free module of deal.II. And what is it? Why do we have it? And what's the motivation? So matrix-free algorithms, that's a pretty hot topic nowadays in HPC, high performance computing. And the reason is, like, when you look at typical finite element programs, typically people tell you, well, the solver is the most expensive part. And when you go to large scale problems, you say typically that you have an iterative solver, which is taking most of the time. And when you look inside of that, so you try to find out in HPC, what is the limiting resource? And you find out, well, most programs spend a lot of time in matrix vector products. And the traditional finite element way of doing things has been the so-called sparse matrix vector product. So you have assembled a matrix, sent that matrix to Trillinos, some solver, maybe some multigrid preconditioners, algebraic multigrid, and you solve that. But when you look inside, you get a very bad performance in terms of what you can achieve, because sparse matrix vector product, as I outline here in my slides, it has a very low arithmetic intensity. So it means that for every matrix entry that you load from memory, you do only 2 operations. So you do a multiplication and then addition, because you multiply by the vector entry and then you add it to some sum that you do over the row of the matrix. And the intensity is around 0.16 and 0.25 flops per byte. And when you compare this to the hardware, it means that, well, actually, hardware can do between 3 and 20 flop per byte, depending a bit on which hardware we're talking about. So you really see that there's a factor of 10 to maybe even 100 between what your hardware could do in terms of computations and between what you can achieve because there's another limit. And the limit is the memory bandwidth of the hardware. So you could say that the sparse matrix vector product leaves the resources for computing unused. And that's something which people call the memory wall. So meaning that there's a barrier, not in terms of how fast you can compute, but in terms of how fast you can get the data from main memory into the CPU for computing. And of course, then the idea is, well, how do I relax my limiting resource? Well, I need to go away from my matrix. I choose a matrix-free algorithm, which just means I compute more and I transfer less from memory. And I have two graphs here on the right-hand side of this slide here, which show you, well, the one is how many bytes per degree of freedom I do for different degrees in my finite element approximation. And the other one is showing how many operations I need to do. And matrix-free, if you go to lower order finite elements, you see matrix-free are doing more work because, of course, I don't use the pre-computed stencil, but I kind of use something which I evaluate integrals on. So that's something I need to be aware of. However, if you go to higher order matrix-free, allow you to do some tricks. And this is an activity we do in deal.II. There's also many other projects, like in the United States, Exascale effort, the SEED project is a very big partner to us. We don't directly collaborate, but we talk to each other quite often, which is also about discretizations. So what is a matrix-free algorithm then? Well, how do we do it? The way I think of it is a way of integrating and kind of just merging the assembly and the matrix vector product in the iterative solver. So what would it be? Well, I go about and say, instead of assembling a matrix first, and then in another part of my program, using it in a matrix vector product, I just do this assembly part on the vector that I get as an input. So I go in my loop here, and of course I have two implications on doing that. Inside of my loop, I'm loading the elemental unknowns. So that's what I do here on the right-hand side. I load these unknowns. I do my integrals on the element, and I don't even form a local matrix on the element level, but I also do this implicitly by integration. And then I get the result back into the vector and make the summation over all cells. Of course, one of the implications is that I need to optimize the loop over cells, which is not the standard infrastructure in deal.II, which is not the optimization level that the standard infrastructure in deal.II has done. So we had to implement something else here. And the other thing is, of course, we want to have data locality in these algorithms. So really we do have good performance. We need to look at how do we access the data, how do we do the performance, and of course, in the end of the day, you're not paid by getting high floating point operation rates, but you're paid by getting many unknowns solved per second, or many problems solved. So that's kind of the throughput is the metric that you're looking at, and not gigaflops or gigabytes per second, for that matter. So how do we do the integrals on the element level? What we're doing is here I have an example of the Laplacian here. So the element matrix vector product is really looked at as an expansion of your product. So when you go about, typically when you assemble, you say, okay, well, I factor out my solution coefficients, put them outside, and then I get a matrix. When you do matrix free, you really get the solution coefficients back into the integral. So that would be the kind of the gradient of the solution UH that you get into. And then you multiply that by the gradient of the test function to integrate over the cell. When you do this integral, of course, you approximate it by quadrature. So instead of an integral, I do a summation. I do a transformation to reference coordinates somewhere. And I end up with something which is now on the second line here, which I highlighted in 3 different colors, because the colors, they mean, well, what I do. So the first part, the purple color, that's the one where I evaluate the reference gradient. So I really factored out the gradient with respect to x into a reference gradient and the Jacobian. The Jacobian can move out of that loop. Why? Because the Jacobian only depends on the position where you are. It does not depend on the shape function index, so you can make a summation before that. Then you have geometry, which only depends on the quadrature point where you are. So that's the orange part in that formula. It's the Jacobian inverse transpose, the Jacobian inverse coming from the test function. There's quadrature weights and the determinant because it transformed the integral. So that's all the standard stuff here. And what is interesting is then in the end, when you do summation, so kind of multiply by the test function, it's again a summation in the green part. For all test functions, sum over all quadrature points. So you could write this as a matrix vector notation, kind of having 3 matrices. And if you look at it closely, you will see that there's a matrix S here, which transforms from the node values or kind of the solution coefficients into gradients in reference coordinates. That would be the purple part. I do something at the quadrature point level. This is a diagonal matrix, the W, or block diagonal, where a block is a 3 by 3 matrix on each quadrature point. And then again, I have an S matrix, which is the interpolation back to the sum. And that, of course, is kind of the heart of the matrix 3 algorithm. So you don't really, if you would assemble a matrix, you would compute the product of those 3 matrices. If you do matrix 3, you just multiply one by one. So I first take the purple action, then I do the orange action, and then the green one. So that's kind of this general procedure here. And when I do that, of course, the first question I need to answer is, well, is it efficient? And there's actually tricks you can do this efficiently, because now my S matrices, they're actually having a pretty nice structure because they're tensor product matrices, because we use hexahedral or quadrilateral elements. They have a tensor product structure. So you can really utilize that. So you don't expand that in a big matrix involving all unknowns and all quadrature points, but you can do this with the 1D matrices essentially. And when you look at it, so I have a figure here, which essentially shows you, well, when you look at what happens in these operations, you will see that there is a series of one-dimensional operations. You do interpolations in X direction, in Y direction, and you do successively. And this is something which is called sum factorization. So kind of just saying, okay, well, I take some factors out of the sum and work with others, and it corresponds to a series of 1D operations, and it brings down your complexity. Like in 2D, you would have an operation cost of the number of unknowns on this cell times the number of quadrature points. So this would be a power 4 in 2D in terms of the polynomial degree. When you do sum factorization, you get down the power to the power of 3. Or in general dimension, if you have a naive formula, which would be the last line on the slide here, naive formula says p to the power 2d, 2 times the dimension. When you do sum factorization, you get this to dimension plus 1 in the power. So really go down in complexity. And that's kind of one of the things that explains why matrix 3 methods are actually quite competitive for high order. Of course, these techniques we have in deal.II, they're not new. They've been around in the spectral element community since the 1980s, but it's really something that has been become more beneficial during the last decade because the computer architecture has changed. Of course, again, for sum factorization, we did the decision, well, should we implement it on our own or should we use BLAS or some other things? Because essentially it's just matrix-matrix multiplications. Here's performance. Now I do gigaflops because I have fixed the algorithm here. And you see that our own implementation on a specific machine, which has a peak of a bit more than 1 teraflop, you see that we reach 600 gigaflops for the polynomial degrees we're interested in. It's typically polynomial degrees between 2 and 10, I call it. And at some point we go down because we did not do all optimizations, but the BLAS is really only competitive for very high orders that we're not so interested in. And the difference is, of course, well, BLAS is optimized for big matrices, and there's function call overheads, there's data rearrangement overheads, which really triple it when you have small matrices. And instead in deal.II, we really need to deliver performance for low polynomial degrees to really optimize that part. And that's just what the compiler is doing when we help it a bit with templates, just knowing it the loop bound so it can unroll loops and so on. And now when we go to that, now of course the comparison I started with is how does it compare to sparse matrices? And here's performance, so this is throughput. So in this graph, higher is better. And sparse matrix, that's the black line you see below here. And if you normalize it per core, which you may or may not like, but you see that, well, essentially during the last 10 years, so this is an AMD Opteron, this is a machine from 2010, this is 10 years old. Intel Skylake is the last figure of here from 2018, 17, 18. And you see, well, sparse matrix vector product per core has not actually improved at all during the last decade, which is quite devastating. See that this is not nice. Whereas if you look at matrix 3 algorithms, there has been a pretty big improvement, factor 3, 4 per core. Of course, now the nodes have become bigger. So nowadays in terms of node performance, we talk of a factor of 20 to 50. And we see that, well, they used to be close sparse matrices and matrix 3 when the product was started. This was around the time when we started in 2010, but now we really have a big advantage. So I believe this is really, the time has come that we need to consider these kind of algorithms more because they're really useful. And of course, now we can just do the comparison. Now again, I have the throughput here. I have done comparison between 2 matrix-based schemes, which would be the green line and the black line. And to see that the matrix-based schemes, they degenerate, they become worse, less efficient when I increase my polynomial degree, whereas matrix-free methods, they become even more efficient per unknown. Of course, this is not for the same number of mesh elements, but the same unknowns. Then people argue that high order elements are actually better because you can use fewer unknowns, so you actually get 2 benefits. first get more performance because I have high orders, and then I get more performance because I don't need a affine mesh, because I can use fewer unknowns on higher order methods because they have better convergence rates. So this is a double benefit. And what's the most striking part of this figure is that when you look here, for example, take the right one, which is a complicated mesh. Matrix 3 gets a bit slower on a complicated mesh because I have more geometry that I need to load. But still you see that the performance for luminous degrees 4 or 5 maybe, this is almost 3 times higher than the sparse matrices on linear elements. So kind of they have the same unknowns. Matrix 3 is better. So that's kind of the summary I have here. On the next slide, they are really more efficient than matrix-based method. If you compare the same order at polynomial degrees 3, 4, it's a factor of 10. But even compared to linear finite elements and the same number of unknowns, it's faster. And that's one of the most fascinating parts of matrix 3 algorithms and why I like them. In deal 2, we have 5 tutorial programs now that explain this. Step 37, 48, 59, 64, and 67 for different flavors of it. One of the things which is not there in deal 2 is that the support for all element types, because of course we need tensor products to get this done efficiently. So we can do continuous and discontinuous elements, but we cannot yet do HDFH curl elements. So at some point, we really plan to tackle the Ferrari-Atoma things that we can do it also on more interesting elements to some of the people here. It's not difficult, but we need to do some work there. And what is important, now I come back to the figure I had on my first slide, we really have several ingredients that we brought together. One is the SIMD vectorization, and here on the right-hand side, you see again, throughput. Now I normalize not per second, but I normalize how many operations I can do in a watt that I compute on my system here. So, and you see that when I just use SSE2 here, so there's just a baseline vectorization that you have on all Intel and AMD CPUs nowadays. When you go to the best vectorization that you get on the Intel Skylake CPUs, you get there's a factor of 3 around that you improve in a throughput per watt. And this is really a fascinating number, I think, because it really shows that it pays off to do this kind of optimizations. We had to work on our distributed vector class as well to make it work efficiently. We tried some parts with Trilinos and Betsy vectors, and we found out, well, we have the index translations, which we don't really like. So we really had to do our own thing here because we need direct array access. We ideally want to have contiguous access into the arrays. And that's something which was not provided in the flexibility we needed. And finally, we have an evaluator class, which does collect the things that you don't have to write too much. And this is an example here from the step 37 tutorial, the first tutorial program matrix 3 method. Well, actually, I removed the variable coefficient from that part. But really, when you look at it, well, there is some boilerplate that you need to put around. So we have something which drives an outside loop here. And then when you get into the code, well, essentially what I do, I have an evaluator object. It has a template on the degree. I told you this is important for the efficiency. At least for now, we have not really tried to hide it. We might do it in the future, but we have not yet. And then I say, well, I read my vector U for my input vector. I interpolate the gradients to the quadrature points. At the quadrature point level, I say, well, I take my gradient and I send it back to be tested, queued for testing by the gradient of the test function. So submit gradient means that I want this to get tested by the test function. I just need to split it up a little bit because that's kind of the orange part. That's what I have put into highlights here. And you have the green and the purple parts, which are in the sum factorization part. So they really need to be split out because I want to avoid the quadratic complexity. So that's why I have them here. So that's unavoidable here. So I need to do it in 2 steps. But essentially, the red part is the only thing that matters when you do a different application. I will show you in a second how this looks like. Now, we also have some GPU support for matrix 3. Has been done by several people in deal 2. The thing that we try to do is for GPU and CPUs that they have similar interfaces, but of course they need to have very different implementations. So we try to make it similar. We don't have all functionality on the GPU yet. We want to expand this in the future. But essentially what you see is when you look at the GPU code, you don't see the part which I put away. So it's only the red part that is now interesting here. And you see it looks pretty similar. I mean, I have a pointer here for some reason, but essentially it's a submit gradient and get gradient. So kind of similar things like the gradient of the solution, which would be the get gradient here, and the gradient of the test function that you do submission for. So that's kind of the interface we have. And we have step 64 written by Bruno and Daniel showing how this works. And of course, we could make the simplification. One thing which is different is that the index Q for the quadrature point is in the CPU code, but not in the GPU code. That might be something for improving actually the CPU code, the old code we have, to get it away from that. Okay, what is use cases? So let me now use a few minutes for where we use it and how we use it. So of course, a matrix-free algorithm, what I'd show you is this is a facility to make integration quick. So of course, explicit time integration is the immediate answer to that. Well, I use that because I just have a right-hand side, I just have a residual. If I have simple linear systems, I can choose conjugate gradient with maybe diagonal preconditioner, which works. But many of the established preconditioners like ILU, Gauss-Seidel, and so on, they don't work because I don't have the matrix entries. Well, I should say I used AMG with matrix-free because I just wanted to have it at some point. It turned out to just have a matrix and the matrix-free object. So matrix-free for matrix vector product and the matrix for the hierarchy generation of AMG. So you could do it, but it's not so nice. And the thing is, well, there is other options when matrix-free. Preconditioners for that, this is an active research topic, not just inside of deal.II, but in the community as a whole. We've done work on multigrid methods, like we have used some variants of Jacobi. I'll show you a result in a minute. What is also ongoing in deal.II is we have been working on block smoothers as well. Okay, so what is new in deal.II in the 9.2 release is the SEP67 tutorial program. It's an explicit time integration method for the Euler equation. And it uses high order DG methods. In that particular case, what we have as a default setting is order 5, so polynomials of degree 5 in 2D, 3D. We mostly look at wave-like phenomena because, you know, Euler equations, they can develop shock for certain ranges of the parameters. So that's not done well by DG methods, even if it's called a discontinuous method, it struggles to do discontinuities, just like every other high order method. So that's a different topic. We looked at the waves of that. And you can see in the tutorial program, that's the first program which shows you how to do systems of equations. You can do inverse mass matrices in DG also with matrix-free facilities. And we can also do some overlap of operations in the cell loop of deal.II. So there's really some nice tricks there which get you some performance. And the result that we got, I mean, this is just a throughput number, how many unknowns we can process per second for this particular setup. Even though it's a nonlinear problem, we use over integrations, more integration points than we have shape functions. We get a very good throughput. It's actually 3 times higher than some of the other results that know from literature, even very good groups at DG methods. So this is a good part. Now just let me come quickly to the code that we do when you apply the cell term in the DG method. You see that, well, essentially we have an evaluator. I have slightly different template arguments now because this deal+II, this is because I have a vector value problem or a multi-component problem. I have 5 components in my Euler equations. I have a density, I have 3 momentum parts, and I have an energy. So that's 5. Deal+II here, so you can select this. And then the code, the scatter evaluate part looks almost the same. What is different is now at the quadrature point level, I need my Euler equations. And essentially what you do is, well, I just have hidden away how I implement the Euler equations. It's not important of importance here. What you need to know is, well, I have an Euler flux term. This is a term that if I give it my coefficients of my vector, of my multi-component value variable W, which contains density, momentum, and energy. If I give it that one, it gives me back the flux. And I just need to implement that. So this is physics, so I can just move it to another function. So all the physics people are doing are working into the Euler flux, and I just almost write the same code. The interface terms, of course, they can also be done similarly. We have a DG method, so we need to have jump terms over the interfaces. At interfaces, we have 2 solutions which meet, so we have 2 evaluators from both sides of that. And all we need to specify is how we work at the quadrature point level. And again, it's a 2-liner, essentially, so we have to say, well, we compute a numerical flux, which gets in my value from the evaluator on the minus side and on the plus side. It gives me in also the normal vector, because I need that for the flux evaluation. And then from that, I can compute whatever I need to do. And then this is all. Then I can test it with a test function and send it to the destination. Okay, so that's my program here. Another topic that we're working on in deal.II recently is that we've collaborated with the SEED group. So this Center of Efficient Exascale Discretizations in the US. They have benchmarks where you look at how do high order finite element codes work. And we've done pretty well there. One of the things that I observed here, so this is a graph here. Now I show timings. So lower is better here. And here I have plotted the time on one compute node of my machine. over the problem size. And if you do big problem sizes, like 10 to the 7 unknowns per node, what you observe is that the matrix vector product, which is the green part, it's not the dominant operation anymore because we've optimized it so much that it's not dominating that much anymore. So what you see is taking a lot of time is the orange part here. So these vector updates. What you're thinking as conjugate gradient solver is for free. Everyone is taught, okay, this is a free operation, don't care about it. What we observe is it takes a third of the time. The diagonal preconditioner Jacobi takes a good fraction of my time. My inner products take good time. So this is really something which is fascinating. So it is an expression of memory bandwidth limitations, even though I said I use high order matrix-free method because they reduce the pressure, but they only reduce the pressure on the matrix vector product, the green part, not on the other parts. Whereas if you have an intermediate size, maybe 10 to the 5, 10 to the 6 in between, you see that while the vector updates, of course, cheap because now they can go from the cache, and the cache in the CPU is much, much faster than the main memory. So that's really a big gap here. But the operator typically on the regime where you're actually also coming from main memory. So this is something we wanted to optimize. We did some clever tricks there. It essentially goes to the cell loop of matrix 3 that we have presented, which is overlapping of computations and vector updates. And for that, now you see this is a comparison. The green part is a GPU, the last version of NVIDIA. So they have just recently presented a new one, but this is the version Volta, the one we had in 2018 to 19. And you see that we range with Skylake, even though the hardware is inferior by a factor of 2 to 3, depending on how you count. We almost reach the same throughput. Again, more is better. We reach the same throughput when we go from main memory because we have overlapped the computations with the cache, which is a pretty nice achievement. And of course, this is caching that you utilize here. Okay, finally, I come to my last part, the multigrid part. In deal 2, we have geometric multigrid because we want to have good solvers, which also work for matrix 3 methods. Not just for matrix 3, but they are, of course, specifically attractive there. And one thing I want to show you is this graph here. So this is again a throughput number now for solving the system. And the matrix 3 part is a curve. This is throughput of multigrid. As again, you see there is some improvement because of cache effects. But what is nice in this bigger what I want to point out here is that the black dot here, where I have my pointer now, this is one single matrix vector product with a sparse matrix. The red curve is the full solution of the Poisson problem. And I solve a Poisson problem with matrix 3 tools faster than I do a matrix vector product on a sparse matrix for polynomial degree 4. So this is really something you have to keep in mind. Matrix 3 is really on a different level here because it is higher order and it is optimized pretty well and it works well with the hardware. And now coming to the scalability, this is one of the graphs that I like. This is a scaling experiment on the large machine up to 300,000 cores. And we use high order DG methods. We use multigrid. We use some transfer to continuous elements. We have a hierarchy of smoothers and multigrid cycles. And what you see is, well, you get pretty nice scaling. So scaling down to 10 to the minus 2 seconds for a solver here. In this case, the solver tolerance is not too tight here, but you really see that this is scaling all the way to the largest machine up to 2 trillions of unknowns. So this is nice. It also uses a good fraction of the floating point capabilities of the machine. Another part is that I like is this figure here. This is some figure done by Timo and Konrad, one of the other developers here, deal 2. I see that just look at two graphs here and look at the orange graph with a solid line here and the dashed lines which are blue. And what you see is that, well, the solid orange line uses 8 times as many unknowns as the dotted line. AMG is the dotted line here. So, and the matrix 3 solves approximately 8 times as many unknowns in almost the same time. So this is 8 times more efficient, or 7 times more efficient, you could say. The other thing which is fascinating here is that you see that the green line here, this is a matrix-based GMG solver. It goes up when you go to many cores. And the reason we have investigated this is that it is because the AMG method, the GMG method uses trillions matrices, and they have global communication in a point where you don't want to have it. Well, in the matrix vector product, they have a barrier because that's facilitating their implementation. And you see that it goes up for large scales. Matrix 3 does not do that because we have our own vectors where we implemented the point-to-point communications in a good way. Just a final result here. This is from the CFD research that we are doing in our result. This is now a plot here when you see this is the work on the x-axis and the error, final application error for some flow in 3D. And written in a logarithmic plot here. And so you want to be in the lower left of that figure. It has been benchmarks effort by the community. They have normalized the time so you can compare different computers. And what you see is, well, our lines, the black lines here, they're really below the other curves. And if you look at, this is one of the gaps here. This is an order of magnitude. We are pretty much faster than the other groups in the community here because we have both optimized the implementation, but in that case, we have also had very good work on the application side on doing the right thing in applications. Okay, the last figure. We have also worked on initialization costs. So all of that I said before was how I optimize the solver. When we do simulations, we of course also want to initialize data structure, especially when we do adaptivity. This is something we have not done pretty well in the deal.II 9.1 release. So this is from last year. And you see that there's some operations out. The black line, this is the GMG V cycle, the parts we have optimized. This is initialization. It's orders of magnitude higher, and it's not scaling well. We have done optimizations to that data structures, and you see now they're doing much, much better, except for creating the mesh and partitioning the mesh, which is a difficult operation. Everything else is now scaling almost as well as a V cycle. The V cycle is really highly optimized. Okay, that brings me to the end. I'm running a little bit over time, but I'm sorry for that. But so really, we have good infrastructure, but there is more work to do in Matrix 3. We want to do GPUs, we want to support more elements, and we want to do some more interesting facilities that users can use to get even more performance. Thank you very much.
Awesome, great talk and great overview, Martin. Thank you so much. I think we are pretty good on time. I think we shouldn't spend too much time with questions. So I just saw one by Guido. Can you go back to around slide 10 or 11 where you have megadovs per watt?
Yes, just 1 second. Let me go there. I need to share again.
Sorry.
No problem. It's my fault, not yours. Okay. Yes, this one probably. Megawatts per second. Megadovs per second.
Yes. So the question from Guido was that's on the same machine, or?
That's exactly the same machine. I just compiled with different flags. So just trying what is the highest SIMD width that I allow the compiler to use, because we use intrinsic-based code, so we can select what to choose.
So AVX 512 is indeed worth it.
It's worth it. I mean, yeah. Yes. But one thing you see here is that when you go from AVX from SSE2 to AVX2, this should be a factor of, well, it can be up to 4 because you have FMAs. But you see that there is a pretty big gap because between the two, you really gain a lot from getting wider. From AVX2 to AVX 512, in theory, Intel promised you get a factor of 2, but you don't get a factor of 2 anymore. It's maybe 10, 20%. This is kind of, if you have worked on AVX 512 machines, then you know that they reduce the frequency because it takes a lot of power to drive 512-bit vector units. And you see it in this figure here. Yes, but it's still faster, but not very much.
Daniel Jodelbauer is asking, how do you measure watts like this?
There has been like the Intel machines, they have performance counters. So the hardware has some built-in registers which you can trigger with some tools. In my case, I use the tool Liquid, which is just one performance tool. You can use others. It just tells you, okay, well, I can put a marker around the algorithm in question, and then I can let it output, okay, well, it tells me, well, I use this and this many joules, and then it divides it, and then it gives you watt.
Okay. As a follow-up, could you go to slide 11, where you have the different architectures, the different machines, and how you how you speed up? This one, I thought this plot was really interesting. Can you very quickly comment on the last data point? That seems like a big jump in performance.
Yes, I mean, that's essentially AVX 112.
Okay, good. Okay, that's what I thought. That's the main difference. I mean, you have a few more cores, I guess, too, right? But
yes, but I mean, I divide by the number of cores.
Oh, this is even by core. Okay.
It's even by core, but you really see that AVX 512 does benefit you. I mean, there is another one here, which is of course not super fair, which is why I had the other slide. The 20-core machine, the data point before that, it's a bit low because it has a lower frequency, but more cores. So, I mean, you could, I mean, you have to balance that the clock frequency of the 24-core machine is about 500 megahertz higher, so 20% higher. So you maybe should subtract 20% from this one here, but it's still more than that.
It's still an impressive improvement, yeah.
Yes.
Okay. All right, I think we leave it here to move on to be somewhat on schedule. So thanks again, Martin. And if you have more questions for him later or in the chat,
I will be around.